on database integrity constraints, where some of the database integrity constraints were explained. In case you have not viewed that video, you can please view that one. I have put the link of that video in the description box below. So in this session, we are going to cover the remaining part. So let's see what we have done till now and what we are going to do today. So essentially, I gave the broad meaning of integrity constraints. What are they? What is the meaning? What are they meant to do? What are the different constraints, their syntax and examples? So we already covered the not null constraint, primary key, unique, and check constraint. Some of the portion of check constraint was left, which we are going to do today, and we are going to cover the referential integrity constraint, which is one of the most important constraint, and it is also likely to be coming in the examinations. So in the integrity constraints, we already covered this portion of not null, unique, check clause, and for the check clause we covered the relational declaration portion, but the domain declaration was left. So essentially we discussed that for the check clause, it is a clause which helps us to check the attribute values with respect to a constraint, right? The general form was check and a predicate within the brackets, where predicate is a condition. Now this can be used in context to a relation or a domain. How we use for a relation, we already discussed that. And in case of a relation, if there is a condition P here, then it should be satisfied by all the tuples of that relation. Essentially, the condition can target a particular attribute or a group of attributes, right? So it is not necessary that all the attributes are put into this condition, but the condition should be satisfied by all the tuples of that relation. Now let's see how we can use the check clause in case of a domain declaration. Okay, so here is the example. Let's first see the example. So we have create domain. So I am trying to create a domain named as hourly wage, and the type is numeric 5,2, and the constraint is, now we already discussed that the constraint can have a name or it can exist without a name. So here we are giving it a name, and the name is wage value test. Okay, and the constraint is now this: check value is more than or equals to 6.00. So what is this meaning? So we have a domain hourly wage, okay, and the constraint says that the wage, the value of the wage should always be more than or equals to 6. So the minimum wage value is 6. The wages, the hourly wages cannot be less than 6. So now again, in case of domain declaration, this P, so this is the predicate, right? Value more than equals to 6. Now this P should be satisfied by any value assigned to the variables whose type is that domain. So what I mean from this is, if there is some variable and let's say there is some variable wage, okay, in my relation, and I specify its domain to be hourly wage. Okay, that is, it can only have the values entered in wage can only be from this domain hourly wage. Then all the values of this attribute wage should satisfy the constraint specified here. Okay, let's take another example. So we have create domain account type, that is the domain name. The type is char 10, constraint account type test. Now again the name of the constraint, and what is the constraint? The constraint is check value in saving, comma recurring. Now what does that mean? It means that the account type account type can only have the value as saving or recurring. So no other value is allowed. So what does that mean? Basically, the account types can only be saving or recurring, but nothing else than that. Okay. So again, whichever variable I assign the type as account type, all the values in that variable should satisfy this constraint. Okay. Now, um there is another type of check command which is very important and which we also refer to as referential integrity constraint. So that is basically a type of check constraint in which the check command in one relation actually refers to another relation. Now let's see this with the help of an example without getting confused. So we have create table deposit, and then we have some of its attributes with their types, and then we have check branch name in select branch name from branch. Now just try to understand what we are doing here. We were defining a table deposit, right? But within it we wrote a check constraint where the constraint says that branch name should be in one which exists in this list. And what is this list containing? This is containing all the branch names from the relation branch, right? All the branch names from the relation branch. So basically, deposit can only have the branch names which already exist in the relation branch, right? So this is something very similar to that of a foreign key concept, right? And there is where the referential integrity constraint come into picture, right? Because what happens in a foreign key constraint, we say that foreign key can only have values which already exist in the primary key attribute it is referencing to, right? So if we have, let's say, a table here, and let's say we have, okay, let's say we have a table here, department, okay, and we have department ID, and we have department names, let's say names, and then this is the primary key here, right? And then we have another table, we have the student table here, student table, we have student ID and department ID and other attributes, let's say. So over here, student ID is the primary key, right? Then what is the department ID over here? It is a foreign key referencing to department ID in the table department. And we can clearly say that student dot department ID will always be a subset of department dot department ID. That is, the department IDs present in student will be the ones which already occur in the department table, because department table consists all the existing department IDs. The complete set of department IDs are present in the department table. So the student table cannot contain any department ID which does not exist in the department table. Okay, and that is the main objective of having the referential integrity constraint, that we, by mistake, we do not enter any new department ID in the student table while inserting the student records, which actually does not correspond to any department we have already created in the department table, right? So over here we have explained two things. First, what is a referential integrity constraint, right? And second, what is the relation between a foreign key values and primary key values? And another thing, third thing which we have defined over here is that What is actually the purpose of having a referential integrity constraint, right? That we do not add any new value in a table which has the foreign key, right? Which is the student table in this case. We do not add a new value in the department ID, which is not defined in the department table, which has all the viable department IDs. Okay, let's move on. So now let's see what is a referential integrity constraint. I already gave the overview. So it is basically used to ensure that a value that appears in one relation for a given set of attributes also appears for a certain set of attributes in another relation. Okay. So I hope you're able to refer back to this with the help of our example, that the value that appears in one relation, which is our student relation, for a given set of attributes, right, for a certain students, and what was that value, which was department ID, also appears for a certain set of attributes in another relation, which is department relation, and we have department ID there. So it is also named as referential integrity constraint or subset dependencies, and it is represented by a foreign key declaration. Now let's see the syntax, how we represent it. So let's suppose I am creating a table account. I will write create table account. Then I'll name all the attributes in that table. Okay. And it will have an attribute, let's say branch name, and then I say that this branch name is a foreign key. So how do I write it? I write it as foreign key, and in the brackets I write the attribute name, which is branch name, references to branch relation. Okay, now what does this mean? This means that the branch relation also has an attribute. Okay, let's make it simple. We'll say that the branch name has its primary key, which is equal to, or which is the superset of the branch name which exists in this table. Okay. Okay. Then how can we represent this thing, which I already explained in the form of mathematical expressions? So we will write that to express this constraint using this example. Okay, so I am writing this constraint in the by using the terms used in this example to simplify it a bit. So we say that for each tuple t belongs to account, so for all the tuples in this account relation, there exists a tuple z which is present in the branch relation such that T of branch name, tuple's branch name, the tuple present in account relation, its branch name is a member of, okay, is a member of or is already present in the branch name attribute of branch name attribute values of branch. So basically the branch name which is present in account is already present in the branch relation. Also, we can say that account.branch name, that is the attribute values of branch name in account, are a subset of branch.branch name. I've already explained this. So basically this is our primary key of relation branch, and this is the foreign key of relation account. And we already said that foreign key values are the set of foreign key values is a subset of the set of all the primary key values. Okay, and without this constraint, what if we do not apply this constraint? Then we may have a branch name in the account relation which does not exist in the branch relation. Okay, so which will be having a loss of database integrity, and which will be creating our database inconsistency, which will be leading the database in an inconsistent state. Okay, let's see some more examples. So these are complete examples with all the attribute names and everything. So let's see what we have over here. In the first example, we have create table student. We have a student table where we have the different attributes representing a student, which are student name, student city, department ID, course ID, instructor ID. Now just as a practice, if you don't see the things, the constraints in this table, just try to guess what could be the primary key over here. So a student name, student city, there can be two students with same names in the same city, right? So we need some other attribute as well to have the primary key. Department ID, okay, again there can be two students from the same city in the same department, right? But then if they are taking the same course, right, if they are taking the same course ID, it is very unlikely. And if they are being taught by the same instructor, now it is also very unlikely. But a course, we assume that uh, in this case we assume that, okay, a course can be taught by two instructors, right? And for a particular section, generally for a particular section only, the same instructor teaches a course in a particular year. Okay, so uh, in this case the primary key for this example which is written here are is a combination of student name, student city, department ID and course ID. Okay, then what we have as the foreign key over here is department ID. Department ID is a foreign key which references to department, because department will be a relation which consists of the complete set of department IDs. Similarly, course ID is a foreign key which references to course, because course will be a relation which comprises the information of the complete set of courses a department or an institution offers, right? So it will have the complete set of course IDs. Then similarly, instructor ID is a foreign key which references instructor, because instructor relation will comprise of the instructor IDs of all the instructors which are offering any course. Okay. Now let's see the next example which we have, create table depositor. So we have a depositor relation here. We have the attributes as customer name, account number. So the primary key is customer name and account number, the combination of both, because because this is a depositor, right? So a customer can have multiple accounts in a bank. So we can have same customer, we can have multiple records, multiple tuples of that customer over here. So we cannot say the customer name is a primary key. So we took a combination of customer name and account number in this case. And then what is the foreign key? So we'll have the foreign key customer name which references to customer relation. In the customer relation, we'll have the complete details of all the customers, all the customer names which are linked to that bank. Okay, and similarly foreign key account number references account, because in that account relation we'll have the complete set of account numbers of the accounts which exist in that bank. Okay, now let's go into deeper details of integrity constraints. We've already studied the different integrity constraints, but we also have some kind of clauses which refer to some actions which we perform using those integrity constraints on the database. Now what happens is, first of all, let's see what we have as the example in this slide. We have two relations. The first one is instructor and the second one is student, right? We have the student relation and the instructor relation. Clearly we can see that instructor ID in this case in the student relation is foreign key which is referencing to the primary key instructor ID in the instructor relation. Okay, now let's suppose I perform a delete operation in the student table. Okay, or let's say I perform a delete operation in the instructor table, then how will it affect the records present in the other table? That is what we are going to study today. Okay, let's say if I perform a delete operation in the student table, let's say I delete the first tuple, which is Sham Bihar ECE course ID 2 instructor ID 1. Okay, so I delete this one. So will it make any change to the instructor table also? So will I require to make any change in the instructor table to make sure that the database is in a consistent state? No. Why is the answer no? Because because our instructor table is independent of any action being performed in the student table, right? Because instructor table does not have any foreign key which is referencing to any other table. It only has a primary key and another attribute which is instructor name. Okay, now can we say the same for making changes in the instructor table? Essentially no. Let's see what happens if I delete the first record in the instructor table. So let's say I delete this. Then what will happen? Now I have deleted the instructor ID 1, instructor name Ramanujan from instructor table. Now if I say that there is a student Sham who is being taught by instructor ID 1, and if I see now, if I refer back to the instructor table to check the instructor's name who is teaching Sham, I won't be able to find the instructor name because that instructor's record has already been deleted. So therefore, we will say that database is an inconsistent state, and in order to resolve it to a consistent state, what would I have to do? I will have to in some manner I'll have to remove this information. Now, how do I remove that information, or how do I make sure that whenever I make any changes to the instructor table, it does not lead to a database inconsistency? I have certain checks, certain actions, okay? And those actions we are going to study today, okay? So we have first of all two actions which have different operations which are performed, which are seen in the combination of different clauses which I have referred here. So the actions are on delete or on update. Either I delete any record in this instructor table, which will create, in that case I'll have to make sure that the certain changes are done to the student table so that database is always in a consistent state. Or if I update, I need to make sure that those updations are eventually moved to the student table, or some action is performed so that the database is in a consistent state. Okay, so we have different clauses which say that we use them as on delete cascade. Now what does this mean, on delete cascade? Now it means that on delete cascade means that, for example, if I delete this record instructor ID instructor name for ID 1, then the record present in student table which is referring to this instructor ID should also be deleted. Okay, that is the meaning of cascade. But then in that case, what will happen is we may lose some additional information, right? Because if I delete this record, what will happen is I am also removing the information of student Sham. So data loss is occurring because I won't have the information about Sham, that what was the student city, what was the department ID, what was the course ID. So essentially that information is also getting lost. Okay, so what are the different alternatives then? We can have on delete set null. On delete set null. Now what does this say? This says that if this instructor ID is removed from instructor table, instructor ID 1 is removed from instructor table, I do not need to remove the entire record from the student table, I can just set the instructor ID as null in this case. Okay, so this saves us from the issue of having data loss, the unnecessary data loss, because now I have the entire information about Sham, because Sham was not taking any other course being offered by any other instructor. Okay, then another possibility is to on delete set default. To set this, to set the instructor ID to any default value. Okay, the default value which has been specified in the relation, or which has been specified in any context, that what is the default value. For example, set the default value as 0. Okay, and we know there is no instructor ID as 0, and it has been defined that instructor ID 0 is a default instructor ID, or you can also have null as an as default instructor ID for the student table. Okay, not for the instructor table, right? So for the instructor table, you can just put instructor ID, not null constraint over here, but you already have the primary key, so it takes care of the not null thing, because primary key, as we already studied in the previous video, it is a combination of not null and unique constraint, right? So it will not allow you to put null value in the instructor table, but you do not have the same constraint in case of student table. It can be null, it can be 0, it can repeat as it is repeating in this case. Okay, no, it is not repeating because the student names are different, but you can have two students, right, being taught by the same instructor, right? Sorry, you can have the same student being taught by two instructors. No, it is getting repeated over here also. Okay, fine. Yeah, it is getting repeated. So yeah, it is not the primary key over here, so it is allowed, right? In case if it was a primary key, it would have not been allowed over here. The repetition would not have been allowed. Okay, then let's see how we do it when we have the update command. Similarly, if we put update on update, so let's say I change the instructor name, right? So is it going to affect the student table? No, because instructor name is not present as a foreign key in the student table. So only if I change the instructor IDs, it is going to affect the student table. So this is also an important point to note, that the student table will only be affected if the foreign key attribute, which is the primary key attribute in the instructor table, is changed, and not any other attribute of that table. Okay, now let's see if I update the instructor IDs as, say I update all the instructor IDs and I change them to INS1, INS2, INS3. Of course, the type needs to be character over here, because the integer, if it would have been defined as integer, I would not have been able to make this change. Okay, and this as instructor 4. Then what should we do in order to, in order to keep the database in a consistent state? We can make the same changes, we can make the same updations in the next table. So the most ideal operation in this case should be on update cascade. On update cascade means make the same changes to the second table which are being made on the first table. So if I perform on update cascade, I'll change this to INS1, change this to INS2, and so on. Okay, and then on update set null will be what? On update set null. So if I have updated this as INS1, I should set null. I should set null over here. But then will it keep the database in a consistent state? No. Why? Because the IDs are different. Okay, so you also need to make sure that which kind of clause will actually help you to keep the database in a consistent state. Similarly, on update set default will also not keep the database in a consistent state in this example. So which kind of clause you need to apply will depend on the type of change you are making to your database. Okay, and what if the constraints are not present initially in the create table? We can add them using the alter table command. We can write alter table, table name, add constraint. So alter table, let's say alter table instructor, add the, let's say, foreign key constraint, right? Or add the primary key constraint. So alter table student, add foreign key instructor ID references instructor. Okay, in that manner we can do that. Okay, that's all for this session. We have covered all the integrity constraints, referential integrity constraints. We have studied them thoroughly with the help of syntax and different examples and different variations in which they can be used. I hope this video would have been useful for you. If in case it was, please press the like icon below. Also let me know your feedback in the comment section below. If you want me to create a video on a specific topic, you can please post that in the comment section below. I keep following your comments regularly, so I'll post the video as soon as possible. So I'll get back to you in the next video on an interesting topic. Till then, stay tuned, keep learning. Thank you.